My YouTube channel. Today I'm solving Leetcode question 685, redundant connection 2. In this problem, a rooted tree is a directed graph such that there is exactly one node, the root, for which all other nodes are descendants of this node. Plus, every node has exactly one parent, except for the root node, which has no parent. The given input is a directed graph that started as a rooted tree with n nodes, with distinct value from 1 to n. With one additional direct edges added, the added edge has two different vertices chosen from 1 to n, and was not an edge that already exists. The resulting graph is given as a 2D array of edges. Each element of the edges is a pair of ui vi that represent a directed edge connecting nodes ui and vi, where ui is a parent of node vi. Return an edge that can be removed so that the resulting graph is a rooted tree of n nodes. If there are multiple answers, return the answer that occurs last in the given 2D array. So compare with the previous question, the redundant connection 1. Here, so this graph is a directed graph with directed edges from U to V. And then it has a definition for tree. So the tree means, okay, there is exactly one node, the root, for which all other nodes are descendants of their nodes, which means like, okay, from this root point to some nodes, and then that node, the node this root point to may point to other nodes as well. So which means like all the other nodes are descendant of this root. Plus, every node has exactly one parent. So if let's say if a node has two parents, then it violates the definition for rooted tree. So let's take a look at the example to better understand the problem. So in this question, so 1.2, 1.3, 2.3 as well. So it forms a cycle. So that's why it violates the rooted node. So it forms a cycle, and then also in this cycle you can see, let's say 3 has two nodes pointing to this, pointing to it. One points to it, and then 2 also point to it as well. In the example 2, so there is a cycle, 1.2, 2.23, 3.24, 4.1, 1 also points to 5. So this 1 is supposed to be the parent node, or the root node. So here the answer should be delete 4 and 1. So because this one forms a cycle, and then in this case, the edge 4, 1 occurred last. So that after we delete the edge 4, 1, so we break this cycle. So how to solve this one? So the overall idea is still trying to use union find, but we need to utilize a modified version of the union find. I mean, the implementation for union find is still the same, but like how we use this union find, we need to modify it a little bit. So because for union find is originally designed for undirected graph, let's say undirected edges, but in this problem, the redundant connection 2, the complexity is added by defining a directed graph. So to solve this problem, we need to actually think about 3 different scenarios that could violate the rooted tree definition. One of the scenarios is there is a cycle, but no 2 edges pointing to the same node. So in that case, out of all edges forming the cycle, we just delete the last appeared edge. The second scenario is there is no cycle, but we have 2 edges pointing to the same node. So in that case, out of the 2 edges pointing to the same node, we delete the last appeared edge. Because in the definition we said every node has exactly one parent. And then in that case, in the second case, there is no cycle, but one node has 2 parents pointed to it. So in that case, we need to delete one of the parents, and then we delete the last appeared edge. In the third scenario, we have a cycle, and we also have two edges pointing to the same node. In that case, out of the two edges pointing to the same node, the two parents, we delete the edge in the cycle. So basically, scenario one is, okay, there is a cycle. We only need to take care of the cycle. So which is pretty similar to how we did that for the redundant connection one. And then in the second scenario, there is no cycle, but still two edges pointing to the same node. So still violates the definition of the rooted tree. So in that case, we need to delete the last appear edge out of those two edges pointing to the same node. And then the third scenario can be considered as a combination for 1 and 2. In this case, we need to delete the edge that pointing to the same node, and then also that edge in the cycle. So once we figure out those three scenarios, the problem becomes much easier to solve. But like the difficulty of this problem is trying to analyze and then figure out those three different scenarios. So the idea is assign two edges pointing to the same node to edge 1 and edge 2. So we first identify, okay, if there is two edges pointing to the same node. If there is any, we just assign those edges to edge 1 and edge 2. So, and then remember that the edge 2 occurred after edge 1. So if no two edges pointing to the same node, then the default value for edge 1 and edge 2 are just none. And then we perform union find operation. When we perform the union find operation, we leave this edge 2 alone. So we do not consider this edge 2. So basically, by iterate through all the provided edges, if that edges is edge 2, then we just ignore it. We do not perform union operation. But if we find, let's say, the edge, and then for the rest of the edges, we just perform union find. If we find an edge E with nodes already in the same subset, so which means if we add the edge E to the graph, then we will form a cycle. So in this case, we consider, okay, so if the edge 1 is not none, so in this case, the edge 1 is in the same cycle as edge E. Our answer should be edge 1 because we want to delete the node. Not just like for the node in the cycle, but also that node is one of the two edge. That edge is one of the two edges pointing to the same node. So in this case, let's say in the line 14, we find an edge, and then if we add that edge to the graph, we will form a cycle. In this case, we consider, okay, if our edge 1 is not none. So in that case, the edge 1 appeared before, and then edge 1 is also in this cycle. But edge 1 is also pointing to the same node as another edge, as the other edge. So it's one of the two edges pointing to the same node. So in this case, it's our scenario 3. We need to delete edge 1 instead of edge E. Because if we delete edge E, we only break the cycle, but we are not solving the problem that there are two edges pointing to the same node that violate the rooted tree definition. So in this case, we need to delete edge 1 if it's not none. But if edge 1 is none, then we know that it's our scenario 1. We have a cycle, but we do not have two edges pointing to the same node. In that case, we just simply delete edge E. And then if we after we perform all the union find operation, we still haven't found a cycle. So in that case, it left with one scenario. We need to delete edge 2 because that's one of the two edges pointing to the same cycle in the scenario 2. And then it's the last occurred edge. So when we assign the edges to edge 1 and edge 2, the edge 2 occurred after edge 1. So that's the overall idea for solving it. So let's code the problem. We first need to code the unit find. I have a separate video for explaining the unit find in details. So right now I'm just like code the optimize the unit find solution. So for unit find, so we have to define the number of elements, that's n, and then we have a default dictionary. So self.parent. At the very beginning, every node's parent is itself. So I for I in range 1. Remember here, this node is denoted by distinct values from 1 to 0 instead of from 0 to n minus 1. And each node just have one child right now. And then let's code the find function, find self. So basically for this find, it's given the element x, find its parent in the subset. Well, this x is not equal to parent x. This is path compression. It's pretty standard. So this path compression is one technique to optimize the naive unit find implementation to speed up the runtime. So if you have any questions about the unified implementation, just check my video on unified. You can find that video in this playlist. In that video, I explained the unified in details, basically how we went from the naive implementation of the unified to the optimized implementation and why we implemented that way. So then we call the union. So basically given x1 and x2, we just perform a union operation. So we first find their parent, use the find function we just coded. So if P1 equals to P2, which means, okay, those two already been unioned, so we return false. It indicates, okay, x1 and x2 already unioned before, already in the same subset. Else, then we compare. So if self.rank P1 is greater than self.rank P2, then self.parent P2 equals self.parent P1, equals P1. And then we also update the rank. Else, P1's parent is P2. Then after perform the union, we just return true. So in that case, first find the two two edges. First we want to find the two edge pointing to the same node. So basically, by initialize them to none. So edge 1, edge 2. And then we also keep track to point 2 equals the dictionary. So for edge in edges, if for u v in edges, if point 2 v in point, sorry, if v in point 2, this means, okay, we already have an edge pointed to this node, and now we find the second edge pointing to the same node. So in that case, our edge 2 equals to u v. And then our edge 1 equals to point 2 v and v. Okay. And then we add that to point 2 u, but point 2 v equals u. So that's kind of how we assign the point 2. So basically point 2 is a dictionary. So with the value, key is the v, value is u, each edge is represented by each edge uv. So for each edge uv is represented in this point 2 with key v, value is u, to denote, okay, what node points to this node v. So in this case, for uv in edges, if this v already in point 2, basically means there's a one edge point to this v, then we assign, we retrieve that starting node u from this point 2 and assign to edge 1, and then we assign the current uv to edge 2. So this one is the edges. Out of the two edges pointing to the same node, this edge 2 occurred last. And then we update our point 2. So, and then after that, let's perform union find. For for edges, let's say for uv in, for edges, for edge in edges, basically we're first uf equals union find length edges. So it's indicate that the edge this input contains n edges. So that's why our n is the length of edges. So we first initialize union find, and then for edge in edges, we just perform union. If edge is not edge 2. In this case, we perform uf dot union edge 0 edge 1. Else, and then we need to keep track of if this one equals false, then which means we find a cycle. So if not, let's do it this way. So if not, which means okay, we find a cycle. So in this case, we check if this edge 1 exists or not. If edge 1, which means this edge 1 exists, then we return edge 1. Else, the edge 1 not exist, we return this edge that's forming the cycle. And then if after loop through all the edges, we didn't find a cycle, in that case we know our answer is edge 2. Let's run the code. Oh, name parent is not defined. So here I'm missing self dot. Okay, we passed the single test case. Let's submit the solution. Okay, cool. So this is our solution for the redundant connection tool. So basically, the idea is we first analyze there are 3 different scenarios that violate the rule of the rooted tree, and then we analyze how we are going to actually delete the edge to handle each different scenario. And then the overall idea is still perform the union find. So that's why my code starts with a standard union find implementation. And then basically we want to first identify the 2 edges are pointing to the same node and assign them to edge 1 and edge 2. There will be none if there are no 2 edges pointing to the same node. And then for each node, as long as that node for each edge, as long as that edge is not edge 2, we just perform union find operation. And then if we find a cycle, and then we check, okay, do we have edge 1? If edge 1 is not none, then we return edge 1. Else edge 1 is none, then we return this edge. And in the end, if we did not form a cycle, then we just delete edge 2 because that's the edge occurred last out of 2 edges pointing to the same node. Also, so again, for the detailed explanation of the union find implementation, please feel free to check my YouTube video on the union find. You can also find that in the same playlist. Thank you.